Let's discuss grounding considerations for a 3 kV single-phase 480 to 240 volt transformer supplying only 240 volt loads in an industrial environment. The question is whether to ground the midpoint of the phase tap connection to earth, given that a grounding electrode conductor is already installed from the transformer case to the grounding electrode. The answer, in this specific scenario, is to leave it alone and not ground the midpoint. Firstly, understand the basic configuration. The single-phase transformer has a primary winding connected to the 480 volt power source and a secondary winding providing 240 volts to the load. Since there's no neutral connection and only 240 volt loads are served, the two secondary windings are effectively floating with respect to ground. There isn't a neutral conductor, and therefore, no inherent ground reference within the secondary circuit itself. Secondly, consider the impact of the grounding electrode conductor connected to the transformer case. This establishes a ground reference for the transformer enclosure, providing a path for fault current to return to the source in case of a ground fault within the transformer itself. However, this connection does not, in itself, create a ground reference for the 240 volt load connected to the secondary windings. The load remains floating with respect to ground. Thirdly, explore the potential consequences of grounding the midpoint of the phase tap connection to earth. While it might seem like a way to establish a ground reference for the load, it would actually create a short circuit between the two secondary windings. This is because the windings are designed to be floating relative to ground. Grounding the midpoint forces one leg of the 240 volt circuit to be at ground potential, while the other leg is at 240 volts relative to ground. This potential difference directly connected creates a low impedance path for current to flow, leading to an overload condition. This overload can severely damage the transformer and create a safety hazard. Therefore, it's imperative not to ground the midpoint of the phase tap connection in this configuration. The system is intentionally designed to operate with the transformer and the load floating with respect to ground. This approach ensures safe and efficient operation in this specific scenario, where only 240 volt loads are supplied and no neutral connection is present. Now let's address the related question regarding the voltage to ground in an ungrounded 480 volt system with no neutral connection or line to neutral loads. In such a system, the voltage to ground is considered to be 480 volts. This might seem counterintuitive, but it stems from the absence of a ground reference point within the system itself. Since there's no grounded conductor, like a neutral, to establish a 0 volt reference, the voltage between any conductor and ground can theoretically reach the full phase-to-phase voltage, which is 480 volts in this case. While the equipment grounding conductor provides a path for fault current, it doesn't establish a stable ground reference for voltage measurement purposes in a normally operating ungrounded system. This is a key distinction. The equipment grounding conductor ensures safety during fault conditions, while the absence of a grounded conductor dictates the voltage to ground characteristics during normal operation. In summary, for the initial scenario with the 3 kV single-phase transformer, grounding the midpoint of the secondary winding is incorrect and dangerous. The transformer and load should remain floating. And in a broader context, the voltage to ground in an ungrounded 480 volt system lacking a neutral connection is considered to be 480 volts.